welcome to the chemistry channel. So in the last video we talked about energy, work, heat, and temperature. And in this video we're going to be putting all of these variables together in the first law of thermodynamics. So to begin, let's talk about what gives an object energy. So what types of energy can an object have? So one type of energy that an object has is associated with motion. So imagine a ball soaring through the air at a certain velocity. The energy associated with this ball is kinetic energy, or the energy associated with motion. And the kinetic energy of this ball is equal to the mass of the ball times the velocity squared over 2. The second type of energy that one could have is potential energy. And potential energy is just stored energy. So an example of potential energy could be gravitational potential energy. And for this, imagine a ball being hung over a certain height from the ground. So it's a certain height from the ground. And the potential energy associated with this height is equal to mgh. So an object can have potential energy or stored energy. However, there's other forms of energy as well. There's vibrational. In other words, an object can be vibrating or oscillating. There's also thermal energy. There's rotational. An object can be rotating. There's energy stored in bonds, as well as in interactions. So there's energy all over the place. And all of these forms of energy are summed up into one common group of energy. And this group is the internal energy. So the internal energy. So what is the internal energy? The internal energy is all the energy that the atoms and molecules of a system possess. So it's all the energy that the atoms and molecules of a system possess. So what is a system? Now, a system is something very important to understand for thermodynamics. So a system is defined as the part of the universe that we are interested in. So one example could be a test tube holding a certain reaction mixture. So let's just say you have this test tube and inside you have this reaction mix. So let's just say we call our system we could call it the test tube and the mixture. So the thing to note is that we define the system. So we define it. So what is outside of the system? Well, what's outside of the system is referred to as surroundings. The surroundings. And the surroundings is every part of the universe outside the system. So it's every part of the universe outside the system. So in this case, the air surrounding the test tube would be the surroundings, and everything else as well. So let's talk about briefly the types of systems And there's three types. The first type of system is called an isolated system. An isolated system is a system that does not exchange energy or matter with the surroundings. So an isolated system is a system that does not exchange energy or matter with the surroundings. The second type of system is a closed system. And a closed system is a system that exchanges only energy with the surroundings, but not matter. The last system is referred to as an open system. And an open system is a system that exchanges both energy, so this is just energy, and matter with the surroundings. So we are actually an open system. Our body is an open system. Okay, so now that we know what systems are and surroundings and internal energy is, let's define the first law of thermodynamics. So the first law of thermodynamics states this, that energy cannot be created or destroyed. It can only be converted from one form to another. So energy itself cannot be created or destroyed. It is conserved. It can only be converted to one form or another. So for example, if you have a ton of kinetic energy, that kinetic energy is not going to be lost as the object slows down. That kinetic energy could be converted into heat or potential energy or other things. So energy is just interconverting between forms. And this first law of thermodynamics is stated with this equation. This equation is the first law of thermodynamics. So we're going to go through what each of these different variables mean individually. So let's first start off with du. So let's start off with the du term. So before we get into du, let's talk about U. So what is U? U stands for the internal energy of a system. So U is the internal energy of the system. And U is a state function. So U is a state function. So let's erase this little dash. So U is a state function. So what is a state function? A state function is a function that is pathway independent. In other words, it only depends upon the final and initial states. So a great example of a state function would be potential energy example. So let's just say you start from a height equal to 0, and then you travel along like this. So you're going all these zigzags. You may go here, there, but you end up right here. So what is the potential energy that you have, or the potential energy change that you get? Well, you don't have to take into account all this travel time. All you got to do is measure the difference in height between these two, between the initial point and the end point. So this is the final and the initial point. And then you can get your potential energy difference. So the same thing can be done for internal energy. So internal energy is a state function. And we represent that internal energy is a state function by putting a d in front of it. So du. So U is the internal energy, and this d is stating that U is a state function. So what does it mean mathematically to have a state function? Well, this requires a little bit of calculus. So when you integrate a state function, so you have your du here, you can put your upper and lower bounds, so your lower bound u1, your upper bound u2. When you integrate your state function, you get an exact differential, or in other words, you get the change in u, which is equal to u2 minus u1. So in other words, your change in internal energy is only dependent on the initial and final state. So that is what a state function is. And that is the internal energy term. So next, let's go to the heat. So dQ. So let's first define Q. Q is the heat. So Q is the heat of it represents heat, while dQ represents the heat gained or lost by the system. So what does this little d, this different type of d look like? So what is this different type of d telling us? Well, this type of d is telling us that Q or heat is a process function. So what is a process function? So process function. A process function is a function that is path dependent. So in other words, you have to take into account the path that this sort of function takes. And mathematically, when you integrate a process function, you don't get a change, you get a value, so you only get Q. So this is what it would look like if you integrate it. And when heat, so this means heat, is gained by the system, Q is positive, and when heat is lost by the system, Q is negative. The last term is work. So let's change our color here. So dW. So now that we know what this dW is, we don't have to go over it. So dW is basically telling us the work done on or by the system. So it's telling us the work done on or done by the system. So what does done on or done by mean? So let's take a look at this. So first recall that work in its integrated form is equal to this. So work is equal to this under constant pressure and in its integrated form. If you're confused about that, see the last video. So work is equal to this, negative P, change in V. So let's first imagine a gaseous system. So let's just say we have a little balloon once again. And this balloon is filled with gas molecules. So let's just say that this balloon, we let it expand into the environment. So let's just say that the pressure inside the balloon is greater than the outside. So let's just say it expands. So let's just put our little gas molecules. So let's just say it expands. So let's get the gas molecules in there. So 1. So it expands. So during an expansion, what happens to the volume inside the balloon? So VI and VF after the expansion. So after an expansion, is the final volume greater than or smaller than the original volume? V final is greater than V initial. So that means that delta V, which is equal to V final minus V initial, is equal to a positive number. So if we plug this into our equation, where delta V is a positive number, we have a negative times a positive, giving us an overall negative value for work. So in this case, we say that work is done by the system. And in this case, work will be negative. So it's important to know this. When work is done by the system, work is negative. And this should sort of make sense to you, because think about it. In an expansion, what's doing the work? The air molecules inside the balloon are doing the work. And that's because they are expanding the balloon so that and they're expanding the balloon against the atmosphere. So the molecules inside of the balloon are doing the work to expand the balloon. Therefore, energy is lost by the system and work is done by it, giving it a negative value. So that's why expansions have a negative work value. So when work is done by the system, work is negative. Now let's do a compression. So let's just say we have our balloon here, and then inside we have our gas molecules once again. And let's just say this time we do a compression. This time P outside the balloon, or pressure outside the balloon, is greater than pressure inside. So what happens is that the balloon will decrease, which makes sense. So let's put in our gas molecules. So let's name this VI for the initial volume and this VF. So in a compression, what would delta V be? Well, delta V is equal to VF minus VI. Therefore, delta V, since VF is less than VI, will be a negative value. And if we plug this into our work equation, we get a negative times a negative, giving us a positive value. So therefore, work is done on the system and it is positive. So work is done on the system, and it is positive. And this should make sense to you, because in this case, the atmosphere is pushing down upon the balloon. Therefore, the atmosphere is inputting energy into the balloon. Therefore, work is done on the system, and work is positive, increasing the internal energy of the system. So now let's put all of this together in a single little table. So, let's make a little table here. And here we'll have du, and then dq, and dw. So du is positive, so the internal energy increases, so it increases. So we have an increasing internal energy when heat flows into the system, and this would be a positive Q. And when work is done on the system, so this would be a compression. And this would be a positive work value. And du has a negative value, or the internal energy decreases. So let's put u here. U increases and u decreases. So du has a negative value when heat flows out of the system. So negative Q, and when work is done by the system. And this would be during an expansion, where you have a negative work value. So the last thing I want to do is to give you the important form of this equation. And we already sort of gave it to you when we integrated everything. So this is the formal version. So the version that you'll see in general chemistry is often this version that I'm about to give you. So let's just assume a reversible system. Oops, let's put our negative here. And when we integrate everything, and we're going to assume constant pressure. So when we integrate everything, you would get delta U is equal to Q minus P change in V. So this is an important form of the equation that you need to know. So this is an important one. And the other important equation is simple. This is how you'll see it in most textbooks. So most textbooks don't present the first law this way. They integrate it for you. So in this case, you'll often see it like this. So we'll just integrate it for you. And when it's integrated for you, you get delta U is equal to Q plus W. So this is the other important equation. So this one is important to know, and this one is important to know. And from here you could see sort of why those positive and negative values increase or decrease the internal energy. because when Q is positive and W is positive, delta U will be positive. When Q is negative, W is negative, delta U will be negative. So that is it for this video for today. I hope I helped you understand the material a little bit better. And in the next video, we're going to be talking about the different types of processes that occur in thermochemistry. So I hope to see you all there. Thank you so much, and hope to see you next time.